Welcome to the webinar on version 4.0 of FDA-iRISK. Almost 400 people are in attendance, some of whom are new users of FDA-iRISK, and some of whom have already been using the previous versions of this innovative tool. We've structured our presentation in a way that we hope will be helpful to all of you. I'm Susan Cahill of the Office of Analytics and Outreach in the U.S. Food and Drug Administration's Center for Food Safety and Applied Nutrition, and I'll be your moderator. Today's speakers are Dr. Jane Van Doren, Chief of the Risk Analysis Branch in the Office's Division of Risk and Decision Analysis. Dr. Huan Chen, also of the Office's Risk Analysis Branch, who is an interdisciplinary scientist with expertise in food microbiology and risk modeling. Yuan is the technical lead on the FDA-iRISK project. Greg Paoli, co-founder and principal risk scientist of Risk Sciences International, who has worked closely with us over the years to develop FDA-iRISK. We'd like to take a moment to thank the Joint Institute for Food Safety and Applied Nutrition, especially Kyle McKillop, for hosting this webinar and for their technical support. The purpose of today's webinar is to introduce FDA-iRISK 4.0, the latest enhanced version of FDA's publicly available food safety risk assessment tool, which went live this morning at 9 o'clock U.S. East Coast time. Today's agenda is to provide an overview of FDA-iRISK, explain how it works, describe new features in version 4.0, and provide a demonstration and examples. Please note that your audio will be muted, but if you have any audio problems during the presentation, please let us know via the Q&A box in the lower right corner of your screen. And with that, I'll ask Jane to provide you with a brief overview.
FDA-iRISK is an interactive, web-based food safety risk modeling tool that enables users to relatively rapidly conduct fully quantitative, fully probabilistic risk assessments of food safety hazards, which inform risk management decisions. FDA has conducted 3 formal external peer reviews of the underlying model structure and mathematical equations, and also has performed beta testing in parallel. At FDA, FDA-iRISK is a tool that facilitates application of science to policy by making that science useful and accessible. The risk assessments we develop with FDA-iRISK inform decision makers and help to ensure decisions maximize public health outcomes. FDA-iRISK informs a variety of types of risk management decisions illustrated on this slide. The tool allows risk comparisons across dimensions such as hazards, foods, practices, and population groups. It predicts risks and compares burdens of illnesses from microbial and chemical hazards. It quantifies and compares effectiveness of interventions, enables users to conduct those what-if scenarios to help risk managers make decisions about what to do. And it separates and quantifies the impact of variability from that of uncertainty in outcomes of risk assessment. The tool provides risk assessors with a structure and mathematical framework within which to conduct risk assessments. For expert risk assessors, it provides an efficient tool to develop complex risk assessments and a platform to share and collaborate with colleagues from around the globe. For less experienced risk assessors, it provides a structured environment in which to build a risk assessment model and ensures accuracy of calculations within it. FDA-iRISK was initially released in 2012. Since that time, we've continued the development of the tool, adding and enhancing features, and responding to the many positive suggestions of its users, peer reviewers, beta testers, and expert panelists. For example, our peer reviewers and others, such as the EFSA risk ranking workgroup, suggested that we further develop uncertainty characterization, and that is among the new features we're telling you about today in version 4.0. FDA-iRISK could not have been developed without the expertise and collaborations of many partners across the globe over the last 10 years. These partners have come from academia, industry, and government organizations. From FDA and the entire FDA-iRISK 2 team, we want to thank each and every one of you for your input into this risk assessment, modeling, and food safety system. We value your insights and the information you provided us to make FDA a tool that can provide accurate results and useful information. On this slide, we provide the names of the institutions involved in the peer reviews and the beta testing. Quite an impressive list, and we thank everyone involved. This is an example of a summary report from FDA-iRISK that illustrates the kind of things the tool can do. Scenarios listed here in the first column are in fact risk assessments. Risk assessments, for example, of Listeria monocytogenes in cantaloupe. For each food hazard scenario, iRISK can predict risk in several different ways or metrics. Total illnesses, mean risk of illness, and DALYs, or disability-adjusted life years. Estimating common metrics such as these allows risk assessors to compare risks across food hazard pairs, across scenarios, even across chemical and microbial risks. In addition to the summary table, FDA-iRISK generates a full report that documents the details of the risk model and results. The full report provides transparency. It can include all the data, information, and rationales the user enters to develop the scenarios. More powerful modeling features in version 4 take it even further. FDA-iRISK can evaluate risk scenarios for multiple foods, such as the inorganic arsenic in juice and rice scenario listed here. And it can consider separately uncertainty and variability. Later on in the demo, Greg will show an example of using FDA-iRISK to conduct what-if scenarios to predict the effectiveness of various interventions for specific food safety problems. With that, I will hand it over to Yuan.
Thank you, Jane. This is indeed a very exciting time for the FDA-iRISK project. We appreciate the opportunity to share the new version with you today. I will discuss how FDA-iRISK works to provide some background and then highlight new features. FDA-iRISK defines risk as probability times consequence according to the Codex definition. We can think of a risk scenario as a collection of elements and data that describe key aspects of the hazard and the food with regard to the probability and extent of exposure and the probability and severity of consequence. Through the specification of a risk scenario, iRISK connects the probability with consequence by using a built-in model structure. This is the model structure for microbial hazard. What we see here, the square boxes represent user inputs. The circular nodes are model outputs. To estimate annual cases, the user needs to provide quantitative data for the process model, consumption, dose response, and a common health metric, which iRISK uses to translate the cases into burden of illness. A number of mathematical equations describe these components to estimate risk. They were the focus of the peer reviews to verify that the equations are adequate. We also wanted to ensure that the computational algorithms integrate the model elements and the data correctly. iRISK uses this structure to characterize the risk from microbial pathogens and from acute exposures to chemical hazards. To predict risk from long-term exposure to chemical hazards, the model structure is essentially the same, except for how consumption pattern is characterized. A lifetime average daily dose, or LADD distribution, is calculated. The number of consumers and exposure duration are also required. As you will see in the new features, in version 4, every model input now allows uncertainty to be expressed. A new feature in FDA-iRISK version 4 is the ability to evaluate chronic exposure to a chemical hazard from multiple foods, as Jane mentioned, such as in the example for arsenic in juice and rice. In a multi-food model, the intake of the chemical is summed over multiple foods over a lifetime, and the intake is combined in a probabilistic fashion. An LADD distribution is calculated for all the selected foods before the dose-response model is applied to calculate the risk of illness. The different underlying structures are what enable users to develop risk scenarios for different types of hazards, different types of exposure for different food hazard combinations. At this time, I will pause for Susan to give a reminder.
Thanks, Yuan. And you in the audience, if you have any questions about what we've covered so far, please drop a note in the Q&A box. We won't reply during the webinar in the interest of time, but we will address them at a later date. Your questions will also help us in the future as we develop future training sessions. And now Yuan will give a discussion of the new features in FDA-iRISK 4.0.
Thank you. This is a screen capture of the homepage of version 4, the web interface where users access, create, save, and share scenarios. You will see new features when you have a chance to log in. By the way, we did not release version 3 because of budgetary constraints. Now we're at version 4 in the development. The category of new features added includes substantial new capacity for advanced modeling, for data uploading and sharing, for results reporting, and enhancement to the web interface and user notifications. Here's a list of new features. The ability to perform second-order Monte Carlo simulation or 2D simulation is new. Another major new feature is the incorporation of predictive microbiology models. The ability to create a descending dose-response curve and the ability to define a diet and dietary shift allows users to evaluate health benefits in addition to evaluating risk. There are several new process types, for example, to evaluate sampling and to evaluate cross-contamination. In version 4, there is greater flexibility in modeling the hazard behavior throughout the food production and processing process. For example, the ability to create parallel process models, linked process models, microbial to chemical linkage to evaluate toxigenesis. There are many other new features, such as exposure-only ranking, and new features behind the scenes to enhance reporting. The relationship of the 7 elements of a risk scenario may look familiar to you. Version 4 now can simulate a risk scenario for single food and a risk scenario for multiple foods. The fundamental approach, however, has not changed. A risk scenario consists of these 7 elements to estimate the number of cases and translate the cases to population health burden. I will take a few moments to go through how simulation works in FDA-iRISK. Let's take a look at a simple model, in this case for a microbial hazard, that consists of a set of parameters for unit size, prevalence, concentration, growth, amount consumed, and so on. Each parameter can be defined as a fixed, variable, or uncertain value. The scenario has 2 variable parameters and 2 uncertain parameters. For simplicity, we use a fixed value to define all the other parameters. I'd like to draw your attention to the variable parameter initial log concentration, which is defined by the distribution triangular 0, 0, 1, and the uncertain parameter uniform 1, 2, and show some numerical details about how the parameters change. In 2D Monte Carlo simulation, the variability parameters change iteration by iteration within one simulation. The uncertainty parameters, on the other hand, do not change within one simulation. They change from simulation to simulation. And so if we look at the variable parameter defined by triangular 0, 0, 1, look at the values in the box. It changes from iteration to iteration within simulation 1. In comparison, if we look at the uncertainty parameter defined by uniform 1, 2, it has the same value within simulation 1, but it changes from simulation 1 to simulation 2. So 2D simulation is the means by which FDA-iRISK explicitly represents a variability and uncertainty in the parameters of the model. Now, in reality, each variability simulation is not just 2 iterations. Instead, it's thousands of iterations. FDA-iRISK evaluates simulation convergence behind the scenes. By design, iRISK has default variability settings and default uncertainty settings to evaluate convergence. The settings define the endpoint to evaluate, convergence criteria and stringency, and how simulations are executed, the number of batches, and the number of tests. These settings are customizable. Advanced users can change the settings and set different degrees of stringency. Having 2D simulation capacity makes it more complex to evaluate convergence. It does require more responsibility on the user's part because computationally 2D simulation can be time and resource intensive. We believe that with training, users can tap into the full power of this and other new features in version 4. And so FDA-iRISK has built-in algorithms to evaluate 2D convergence. First of all, when the user defines a variability-only model or 1D model, iRISK runs simulations using the variability algorithm with a minimum of 9,000 iterations plus 3 tests and evaluates the endpoints. If the convergence criteria are met, the simulations end and the results are reported. When the user defines a 2D model, the uncertainty algorithm also kicks in. iRISK draws samples from each of the uncertainty distributions, executes the variability algorithm, and repeats the process for up to 100 times. It then runs one additional test and evaluates the endpoint. Again, if convergence criteria are met, the 2D simulation ends and results are reported. And the results would look like something like what we see on this slide. What FDA-iRISK can do is reporting risk estimates with uncertainty results. For example, for the salmonella in peanut butter scenario, the summary results will show the total deaths per year in percentile. So the minimum, the maximum, median, mean value, and the interval between the 5th and the 95th percentile. Similarly, results with uncertainty are reported for a multi-food risk scenario, such as the scenario for inorganic arsenic in apple juice, pear juice, white rice, and brown rice. Okay, so that's an overview of the new feature on 2D simulation. The new process types in version 4 are highlighted on this slide. They are mostly for modeling microbial hazards in terms of growth, inactivation, cross-contamination by transfer rates. These new features add to the number of built-in process types previously in the tool for users to choose from in order to describe the effects of different food production, processing, and handling steps. A new sampling process type is now available for both microbial and chemical hazards to simulate the effect of rejecting contaminated products from the food supply. Version 4 supports a wide range of predictive microbiology models to predict growth or inactivation based on user-defined conditions. iRISK provides primary and secondary models for inactivation in linear and nonlinear forms. It also provides primary and secondary models for growth and lag time. For example, the square root model and the relative lag time model. When users define growth by predictive model, there is also an option to not include lag time. The predictive models are defined with a link to the hazard to be selected as a process step when users define the process pathway model. Okay. So what else is new? The option to create a parallel process model is new. This feature is useful in a situation where a food process pathway involves a sequence of steps that are substantially the same, but details may vary over several facilities, operations, or farms in their practices or the degree of compliance. We can use this feature to define a baseline model and add variations as required at one or more steps for a variance. The feature makes the modeling more efficient. Another new feature that makes modeling more efficient is the option to create linked process models. It's not unusual that in a food production, an ingredient or raw material is made into different products. For example, milk may be processed into pasteurized milk, cheese, and ice cream. A fruit ingredient may be used in ready-to-eat salad and frozen desserts. The initial prevalence and levels of bacterial contamination may be the same, but the growth potential may differ under refrigeration versus frozen conditions. So we can use this new feature to create a single upstream model that is then linked to different downstream models. Another new feature I want to talk about is particularly useful in dealing with consumption data. For both acute exposure and chronic exposure, the food consumption amount may vary from eating occasion to eating occasion or from person to person. Typically, a distribution is used to represent variability in the consumption amount. And we can get such a distribution from analysis of consumption database, such as the NHANES, What We Eat in America, and upload the data into FDA-iRISK. And I have an example here for consumption definition in a chronic exposure situation. The live stage is 1 to 7 years. Now in version 4, users can simply click the input button, what you see on the left screen, in the middle of the left screen, and they will be prompted to select a data file, preview the data, and then upload the data. So this new feature is also available to import data other than consumption. For example, data representing OC curves for a sampling plan or concentration distribution data. Before we go to the demo, I'd like to highlight one more new feature, which enables us to compare risks from different diets. The new ability to define a steadily or monotonically descending dose response is useful to represent a nutrient deficiency situation. In this case, the probability of illness goes down as the intake dose increases. But too high a dose may lead to toxicity, where a higher dose leads to a higher probability of illness. This example shows the dose response curves for manganese deficiency on the left and manganese toxicity on the right. Used together, they enable the comparison of risks from these chemical elements among consumers with different dietary patterns, such as different patterns of fruits and vegetable consumption. In this example, a baseline is defined for a dozen foods. You see the definition for the process model for the foods and consumption patterns for these foods. Risk estimates are generated for the baseline and two other diet patterns, half the baseline or 2 times the baseline. Now, the baseline here is a deficiency situation with predicted 143,000 cases in the population. Okay, so over a lifetime, when people eat half the baseline, a greater number of cases is predicted. In contrast, when people eat 2 times the baseline, fruits and vegetables, a much lower number of cases is predicted. And so that's how it works. I'd like to point out the disclaimer here. This example and other examples we talked about in the webinar are for illustration purposes only. The risk estimates will change when users provide different data, different assumptions than those in the examples. With that, I'd like to turn it over to Greg.
Thank you, Dr. Chen. I'm going to provide a short demonstration of the iRISK web-based interface, which I will switch over to now. And I'm going to describe, as Dr. Chen did, for those in the audience who have not yet used FDA-iRISK, but focus most of the demonstration on a selection of new features that are being released today. When you log into FDA-iRISK, you will see a series of tabs across the top of the page. These reflect the 4 primary modes of working with FDA-iRISK: building models, running models, sharing models, and seeking documentation. The Help tab is a good place to start, particularly to view the Quick Start Guide, which contains step-by-step instructions to help you build your first set of models. So the Quick Start Guide literally walks you through step-by-step how to do your first set of models. Similarly, the User's Guide will provide even more detail than that on all of the features of iRISK. One feature that we haven't mentioned yet, but is actually showing up on the screen, is the fact that the user will receive a notification when a simulation has been completed, if they choose to have, and they may also choose to have an email notification if they want to receive the information that way. So I'm just going to clear that now, and we'll look at that report later on in this demonstration. When using FDA-iRISK, most of the user's time will be spent building models within the Risk Models tab. We will spend most of the demonstration time here viewing the implementation of the major new modeling features. Having built or modified a model, the user will then request that the iRISK run the simulation model, including 1 or more scenarios. This is done using the Reports tab. The Repositories tab is used to manage user-to-user sharing of models, with the default being no sharing whatsoever. For example, you can invite a colleague to view one of your models, or accept an invitation to view a model from another colleague. There is no way for another user to see your models unless you have explicitly chosen to share with them. Let's return now to the Risk Models tab to view some of the newly released features. As we've discussed thus far, one of the most substantive changes to FDA-iRISK is the capacity to describe both variability and uncertainty as separate aspects of risk assessment. In the previous version of iRISK, the user was able to describe various model elements as having variability, but was expected to explore uncertainty through the use of a sensitivity analysis. The version 4 release contains the ability for the user to describe both variability and uncertainty using probability distributions. For example, I can add uncertainty to an existing risk model very quickly. I will add uncertainty to the first process model in my list, namely aflatoxin in tortilla chips. I'm going to express uncertainty in the mean concentration of aflatoxin. So I'm going to open up the process model. You will notice that by default, all the uncertainty is absent or not applicable. Wherever there's a quantified aspect of an iRISK scenario, there is an uncertainty option to add the uncertainty, as you can see we've done here. So we've now added uncertainty in the mean concentration of aflatoxin. So we have now described both variability and uncertainty in the mean of the variability distribution. You'll also notice that it's possible very quickly to also delete that same uncertainty if you choose to want to remove it. Now, having added uncertainty to a model, the user now has the option of running the simulation with or without uncertainty dimension. When requesting a simulation, the user can check a box to include uncertainty or not. If the user has not included uncertainty, the box will be replaced with not applicable. So for example, if I now want to run a report on aflatoxin in tortilla chips, I can choose the hazard here, load the available scenarios for that hazard, and as you can see, there's now a box to include uncertainty. So by default, it will not be selected. The user will have to select it in order to run a 2D simulation. So the ability to do second-order Monte Carlo simulation requires some additional considerations, as Dr. Chen mentioned. A second-order Monte Carlo simulation can take hundreds of times longer to run than a first-order Monte Carlo simulation. That means that a simulation that takes a few seconds or a few minutes as a variability-only simulation could take a few hours as a second-order simulation. Users may want to run variability-only models most of the time, second-order simulation models only occasionally, and they may also want to control how long this might take. The new release of FDA-iRISK allows for the user to configure the way in which the convergence of a Monte Carlo simulation is defined, both with respect to the accuracy of the variability dimension, as well as the accuracy of the simulation of uncertainty. This is accomplished by the Simulation Settings tab, which we're in now, in which the user is invited to adjust the stringency with which the simulation must converge to a stable statistical estimate. And you can see that there are various options as to which particular statistics are tested in the assessment of convergence. As you can see, the user has considerable control over the stringency of the definition of convergence. For quick runs, for example here, using this simulation setting set, the user may choose to use the quick run simulation settings. When the analysis is closer to completion, the user might request a more stringent definition of convergence to be more certain of the results, but should expect to wait longer for those results to meet these requirements. In keeping with the increased level of control over the model convergence properties, there is an increased level of reporting of the convergence behavior of the model. So within the report documentation available after the simulations have been run, there is an additional report that is available which provides details of the extent to which the model has converged, or if in the case that it hasn't converged, exactly how that happened and which test was being failed. When simulation model that includes uncertainty has been run, the final report, for example a PDF report, contains details of all of the model elements that were included in the simulation and their uncertainty characterization. And in addition, the final risk estimates will contain a range that corresponds to the impact of the described level of uncertainty. So for example, this simulation was a second order simulation model, and if I open up that report, you will see that the input of the prevalence of a contamination level in this pathogen in powdered infant formula has been described by the user. As a result, when looking at the results, you see that the level of burden of disease is provided, as well as various statistics of the uncertainty distribution of that estimate. So that's an example of the output of a 2D simulation and how to find it. An additional major new feature in FDA-iRISK version 4 is the addition of the ability to do multi-food assessments for chronic exposures to chemical hazards. This is particularly important for exposure to chemical hazards which may be found in a variety of foods. When creating a scenario for chronic chemical exposure or risk, you will have the option to do, so here if I add a new scenario, I have the option of multiple modes of developing models. I can do a single hazard, single food combination, which was the ability that was available in prior versions. You will also have the option to do a single hazard and multiple food scenario, or a multi-food, multi-hazard combination. I also point out here that the user has the option of conducting exposure-only scenarios and now also exposure-only rankings. With this selection, the user is not required to develop or apply a dose-response curve or any burden of illness metrics such as disability-adjusted life years or cost of illness estimates. Some users may be interested only in conducting exposure assessments, perhaps to compare the exposure to a dietary exposure threshold value. Or it could be temporary while the dose-response components of the model are not yet complete. As Dr. Chen mentioned, an important additional feature in the risk modeling environment is the concept of a diet. This capability allows the user to describe a diet, which is a pattern of consumption across foods, and then describe shifts in the dietary pattern. If I look at, for example, at this diet, each of the consumption patterns for each of these foods has already been specified by the user. This mode of creating dietary shifts allows the user to add more foods and also add more shifts in the case where they want to run multiple variations of the diet. In this case, there's a baseline diet, a 10% increase, 20% increase, or a doubled intake of each of these foods that are included in this diet. This modifies the underlying consumption model in a multi-food chronic chemical exposure model. When I look at a risk scenario, I can choose now which of the dietary patterns I want to include. So for the manganese in fruits and vegetables, I can indicate that there are this pattern of foods are included. You can see the list here. In addition, the diet is specified. The baseline will always be included, but you can decide whether to include the 10%, the 20%, or the doubled intake for a particular scenario. In this case, the user would only want to see the baseline and the doubled intake. Moving on now, I'm going to show a few new features that relate to microbial hazards that Dr. Chen described, but I'm going to show you a little bit more of where you would find them and how you would implement them. So version 4 expands on the ability to describe microbial growth and inactivation within a process model. Previously, the amount of microbial growth or the degree of inactivation was specified directly by the user. In version 4, the option is provided to estimate the amount of microbial growth using predictive microbiology models. The same applies to calculating the extent of inactivation through, for example, cooking. So these predictive microbiology models are associated with the hazard element within FDA-iRISK. And if I choose the Corynebacter sakazakii pathogen, I can, you now see what will be new in version 4 is this predictive tab. At the core of the predictive microbiology capability is this predictive tab. The predictive tab accompanies a microbial hazard to define models for growth, lag, and inactivation. A variety of models are available. These 4 models have already been specified for this pathogen, but if I was to add another one, you can see the list that you saw on the screen earlier. I will just cancel that now. For any model added, the FDA-iRISK asks you for the parameters specifically required for that particular predictive microbiology model. So here you see, for example, the parameters expected to be added for the square root biokinetic model. Once models are added to a hazard, they are accessible in any process model built for that hazard. So for example, during the feeding of powdered infant formula and during that holding and feeding phase, there is an opportunity for the pathogen to grow. So in the holding and feeding phase of the process model, we can edit the model. And here you see that this is where you would specify which among your predictive models you want to apply in this process stage. In this case, square root model for lag, square root biokinetic model for growth. The units of Celsius will be applied and the time will be described in hours, and then the user would proceed to describe either as distributions or as single values the temperature and the time associated with that phase in the model. Users also have the ability to define a correlation between temperature and time if they believe one to exist. There is no limit on how many predictive models can be added to the hazard. For example, there may be many different growth models for different media types or different model fits available in the literature. You can build your own custom library of models. The same model can be used in multiple scenarios. So I'm now going to switch to another mode within FDA-iRISK. Version 4.0 gives different options for defining the initial conditions of process models. So in the process model for Corynebacter sakazakii, you can see that multiple parameter sets have been implemented. Just 1 minute, please. One option is to choose just a single set of parameters. Another option is to choose multiple sets of parameters. This particular version choice has been made now. Another version is to choose a upstream process model. This is what we called in the presentation a linked process model. So I'll briefly describe upstream and downstream linked models. In this mode, the user can specify that the initial conditions for the current downstream process model are provided by the prevalence and the concentration of the product at the end of an upstream process model. This, for example, as Dr. Chen described, would be applicable to the combination of milk and many other downstream dairy products. So if that were the case, the upstream process model in that case would be referring to liquid milk, and the current model would be one of many dairy products. When a risk estimate report is requested for a scenario with linked upstream and downstream process models, iRISK will automatically merge the two process models to compute the final exposure and risk estimate. Parallel process models are available for microbial hazards at present. As you can see on the screen, this process model is using multiple sets of parameters. Now the user can define variations of the current process model by clicking on the Copy to New Parameter Set name. So I can create a duplicate process model and then proceed to amend any parameters within that process model that I choose. This applies to the initial conditions as well as the process stages. So the process stages, the process model beyond the initial conditions can also have multiple parallel pathways, as you saw in the diagram in the PowerPoint slide. This lets the user create an alternative parameterizations of the same process model to, for example, represent different suppliers or processors or regions, or study the difference between a baseline scenario and a scenario with various proposed changes at various parts in the process. So for the Chronobacter Sakazaki model that you see on the screen, I've created temporarily parallel models which modify the maximum level of the initial contamination of the infant formula product, as well as the duration of the final holding and feeding period where the microbe might grow. And if I run that model, you see in the report abstract for the model result that it says that there are two modifications in the modified scenario, the reduced maximum initial contamination level and a reduced storage time at the first stage of preparation, the final stage of preparation, rather. Having created parallel process models, they will appear in the report as though they had been different scenarios, but in fact they are run as two separate simulations because of the different assumptions made in the simulation. So as you can see here, there is a dramatic reduction in the burden of disease here associated with just those two small changes, although they are clearly important changes based on the results you see here. So with that, well, despite the fact that there are many other new features to demonstrate, I believe I've run out of time, so I'll hand it back over to Susan.
Thanks for that very helpful demonstration, Greg. And I'd like to remind our audience that the Q&A box is available for your questions, which we'll address not during this webinar, but in the near future. And at this point, Yuan will provide you with a summary and will tell you where to find more information about FDA-iRISK.
Thank you. So as Jane mentioned at the beginning, we designed FDA-iRISK for the agency's own use. We're making version 4 available for the food safety community so that stakeholders in industry, government, and academia, as well as the broader public, can benefit from the tool and the latest new features. Are we good? Okay. We hope that this presentation has made it apparent to you that FDA-iRISK can facilitate the development of quantitative risk assessments. The tool provides a robust database and mathematical architecture to support a majority of the types of calculations typically required. Again, the user provides the data and assumptions based on their knowledge about the foods, the hazards, and the conditions that they are in. FDA-iRISK provides the modeling capacity. We believe that new analysts can use FDA-iRISK to more quickly become capable of developing quantitative risk assessments. Experienced risk assessors may use it to more quickly develop risk assessments and benefit from the advanced modeling capacities. And once the user has entered the data and assumption to describe the required elements of a risk scenario, FDA-iRISK is capable of combining the user's inputs into a fully quantitative, fully probabilistic risk assessment. And so now there is the option to use probability distribution to describe both variability and uncertainty, and the user can have the option to run 1D model or 2D model through Monte Carlo integration to obtain risk estimates for the health burden to the consumer, with the attendant uncertainty results if a 2D model is built. Again, a number of scenarios can be developed for ranking risks across different foods, different hazards, different populations, as well as predict the impact of different food safety interventions, as Greg illustrated. At FDA, we continue to use the tool in a number of ways. We are building new scenarios and expanding a library of data to address risk management questions. We've been using the tool to evaluate risk and the effectiveness of interventions for salmonella in shell eggs, for pathogens and chemical contaminants in produce, and for supporting FSMA, the implementation of the FDA Food Safety Modernization Act. New features in version 4 have enabled us to better utilize existing data sources, such as the FDA Total Diet Study data. We've been exploring ways to connect FDA-iRISK to other modules and other tools to help us answer new questions. And it gives us an excellent platform to collaborate with other agencies, other countries, and the private sector. This schematic might look familiar to you. We like to use it to very broadly, again, tie together the overarching components in FDA-iRISK, which provides a structured, stepwise data entry, documentation, computing, reporting, and sharing environment. In this schematic, we see how the user interacts with FDA-iRISK on the left, the activities on the left, what FDA-iRISK does, system integration and automated calculations in the middle, and what happens afterwards in the right. The beauty of FDA-iRISK, we believe, is that you can simulate interventions and change the data at specific points in the food chain. iRISK will look back and give the predicted public health outcomes if the interventions were applied. We hope that over time, FDA-iRISK can capture data from scenarios and outcomes to build a global picture of risks and interventions from data that users have voluntarily shared. To conclude, we want to acknowledge Dr. Sherry Dennis and Dr. Regis Pugh from FDA for their instrumental contributions to the development of FDA-iRISK. As Jane mentioned, we want to also thank the many experts who provided invaluable input to the FDA-iRISK project from version 1 to version 4 over the years. FDA has developed the tool in collaboration with experts inside and outside of government, including scientists from RSI. We want to thank Dr. Emma Harnett and Todd Ruthman, who, besides Greg, are key members of the RSI team. Enhancing and applying the FDA-iRISK system is an ongoing process. We will continue to refine the tool as advances emerge and continue to use it as a means for collaboration as well as facilitate risk assessment to inform timely decisions. For further information, I encourage you to visit the FDA-iRISK portal on foodrisk.org, where you will find the link to the application and links to the technical documents and user guides. You're most welcome to create an account if you are not already a user. With that, I'd like to ask Kyle to provide information on webinar follow-up.
Great. Thank you. We'll be making today's recording publicly available, and we invite you to re-watch and share with your peers. Thank you all for joining today. For more information on the activities of the Joint Institute for Food Safety and Applied Nutrition, please visit our website at gifsan.umd.edu. Thank you.